SLAC, and Deputy Director of Operations for the LSST, the Large Synoptic Survey Telescope. His science interests lie in strong gravitational lensing to make accurate measurements of cosmological distances in order to pin down the accelerating expansion of the universe. This is his third stint at Stanford, having been there twice as a postdoctoral research fellow. Phil got his PhD from Cambridge in the United Kingdom and has enjoyed life in California since being out here in 2003. And tonight will be the second time he's spoken to SFAA. Currently under construction in Chile, the LSST will survey the entire visible southern sky every few days for a decade. The widest, fastest, and deepest view of the night sky ever observed. This vast archive of data will dramatically advance our knowledge of dark energy and dark matter, as well as galaxy formation and potentially hazardous asteroids. Much of the data archive will be available not only to professional astronomers, but also to educators, students, amateur astronomers, and members of the public interested in citizen science projects. This invites us to think about what we mean by exploring the heavens, why we do it, and what we may learn. Join me in welcoming Dr. Phil Marshall.
All right, you're not going to like what I'm going to do next. So you can hear me all right at the back with this. I'm going to try a little experiment if you don't mind. So when I give talks, I like to roam around. But there isn't a roving microphone to go with me, so I need to check. If you're at the back, can you hear me if I talk like this? Yes. You can. And I hear from PJ that the microphone will probably pick me up for the people watching on YouTube later. Okay, let me do the password. I want to take a walk around. No. Yes. Let me just do my password again for the third time. Probably not the last. Okay. All right. Thank you very much for having me. It's very nice to be back with you all. As Linda says, it's my second time out. I'm a research scientist at SLAC, one of your local national laboratories. You should come and visit us sometime. I thought it might be good for me to get to know you just a little bit. We can't do lots of introductions, but I did wonder if you wouldn't mind answering a question for me. It's real quick. I'm going to ask you to express a preference about questions in talks. So the question is going to be, do you prefer it when all the questions come at the end of the talk, or if questions come during the talk? So hands up who prefers them at the end of the talk. Okay, and who prefers them during the talk? Okay, so we'll need to figure out how to handle this. I suggest maybe if you have a burning question that you think the rest of the people in the room would benefit from hearing the answer to, you should put your hand up and ask it at the time it happens, and I'll answer it. And that way, hopefully, it won't be too annoying for the rest of you who prefer it when questions come at the end. And for the rest of you who prefer questions at the end, I'll try and keep things moving so we won't have too many questions. So I hope that's okay as a compromise. But interesting, eh? Half and half. Okay, so exploring the final frontier with the Large Synoptic Survey Telescope. I first gave this talk in Tucson, in Arizona. Frontier town, get it? It's where the LSST headquarters is, and I thought I'd try and relate to them by using the word frontier. Of course, everyone knows what the final frontier is. It's outer space. So this really is a talk about how we're going to try and explore the universe at various scales using this amazing new telescope that we're building. I also like this quote from Carl Sagan here, the frontier is everywhere. I like giving talks to astronomy clubs like yours very much for a number of reasons. One reason is you know exactly what this means, because when you do star parties with the rest of the astronomers out there, perhaps they don't know they're astronomers yet, when you do star parties, you can feel this within you, can't you? That the frontier is right there. All you have to do is look up. Okay, so what does it mean for us to be exploring the universe with LSST? Well, we're interested in questions as scientists, asking questions about the universe, trying to find answers. And really fundamental questions with LSST and telescopes like it. So we're interested in where do we come from, how does the universe work, what else is out there. And I say we, that's we research scientists, but also we citizen scientists, all of us in this room, natural scientists. And so all of us are at some level engaged in this business of asking questions about the universe, figuring out how it works at some level or another. Okay, so exploring the universe. When I first explained to my girlfriend, now my wife, she stuck around, she wanted to know what I did for a living. So I tried to explain about working on the LSST and how it was this amazing telescope that would survey the night sky and make a map of the heavens in some way. And we were looking for new things to discover, as well as making accurate measurements of how the universe works. So she listened to me go on about this for a few minutes, and then she said, "Oh, you're like Magellan." And I said, "What?" Yes, in a way, we are like Magellan. So in the olden days, explorers were sort of how they are in the movies and in stories for you. They had ships. They would get a crew together and they would literally sail off into the unknown and explore the oceans or the jungles or whatever. But they didn't do it with no reason. They also had questions they were interested in. For example, Ferdinand Magellan was interested in the question, is there a way to reach the Philippines by sailing west? And so he proposed, just like we proposed to use telescopes, he proposed to use several ships and to go on a westward voyage to the Spice Islands. So he left in 1517 with 273 crew, came back 3 years later with only 18 returning, including, sadly, not Magellan himself. He didn't make it back. So I tried to explain to Melinda that that's hopefully not how I'm like Magellan on LSST, that I will actually come back when the survey is finished. Okay, so let's think a little bit more about what Magellan and his crew did as explorers. So they tried to sail west from Spain to the Spice Islands. And to do that, they had to go down the coast of South America and find a way past this enormous landmass. And they found it. Their main discovery, the main result of their survey of the oceans, is this little feature here, now called the Straits of Magellan. This is the southern tip of South America, and they found this little way through. So they could sail through that, and they ended up in this whole new other ocean on the other side. Amazing thing. So when they got back, fortunately one of the people that made it back, or at least some of them, were able to transmit enough of the ship's logs for them to make a map of where they had been. And so here's a reproduction of the map that they made when Magellan's crew got back. You can see here's the bit they already knew, the coast of Africa, Europe, and this piece of South America. And then they also knew about these other pieces over here. But after this voyage of discovery, where they found the Straits of Magellan, all of this now appeared to them. This whole ocean of possibility that they didn't know was there before. They now know how far it is across that ocean because they made it to the Spice Islands, the Philippines, through crossing the Pacific. Okay, so the main result then, I think, of Magellan's exploration was this map that now shows the Pacific. So with LSST, we'll be doing the same thing, making maps of the heavens. We've said that a couple of times already. Let's think a little bit more about exactly what a map is. How is a map of the sky like a map of the Pacific Ocean, or a map as we now understand? When you say map to someone, they think, oh, I've got one of them in my telephone, made by Google. And so here's some examples of modern maps. And I like showing pictures like this because you can see the connection here between the data that we take. Here is an image taken from a satellite of the Bay Area. That's data. But here is the map that we can make from that. So maps are simplified representations of data. And more than that, they're representations that help us understand what's there, what's in our vicinity. And they show us paths forward that we may not have realized were there. New ways to get to San Jose, avoiding the traffic, for example. So if you can make a good map, it sort of gives you new directions to go exploring things you didn't realize before. It was true for Magellan, and hopefully you'll see it'll be true with the maps we make with LSST. Okay, I said I like giving talks to groups of astronomers for several reasons. Here's another one. All of you understand exactly what Marcel Proust means when he says that the real voyage of discovery consists not in seeking new landscapes, but in having new eyes. Do you remember when you first looked through the new telescope that you got, or your friend has? It's like having new eyes. You get to see new things that you didn't realize. So here are our new eyes for the next decade, currently being built, assembled. Here's what we're doing at SLAC. We're building the biggest digital camera in the world, so 3,000 megapixels. And it's the size of a small car. Looks a bit like a regular camera, but just a whole lot bigger. And it'll be mounted looking down on the tertiary mirror, which is embedded in the primary mirror. It's 8.4 meters across. So collecting a lot of light over the course of the survey. And the images that we take with this camera, this 3 gigapixel camera, will feed to the data facility that will process 500 petabytes of data by the end of the survey. 500 petabytes is an enormous number. What does it mean? Well, it's about what you need to store a copy of every book ever written in every language currently in use. Huge amount of information. So the observatory will be in Chile, at Cerro. The data facility will be in Illinois, at the National Center for Supercomputing Applications. The headquarters for the whole system is in Tucson, Arizona, and the camera is being built at SLAC. So I thought I'd show you a few pictures of how things are going with the LSST. I know at least one of you is a huge LSST fan. So here's where we are, where we were a couple of months ago. So March of this year, here's how far we got building the observatory down at Cerro, dry mountaintop site in Chile. I like this to show these two pictures. For a long time, we only had artist impressions like this, predicting what they would look like. Turns out the LSST does actually look like that, which is great. You can see that the framework for the dome is now almost complete, and the telescope mount assembly will be on its way soon. Here's a photo of that. Very grainy, sorry, I copied it badly off the internet. But this is a picture of the telescope itself at its assembly facility in Spain. You can see something here of the optics of this telescope. It's a very fast optical system. It has a very wide diameter mirror, but the focal length is actually quite short. So it allows us to take high quality images over a wide field of view, but with a big collecting area to go very deep. So the main thing about the LSST that you should remember is that it's fast at surveying the sky.
What's the F number?
I was just thinking outside. Someone's going to ask me the F number. I think it's about 1.1. So it's super fast. Super fast, but also very big and very heavy. So this thing weighs 300 tons, and it can slew 90 degrees in 9 seconds. 90 degrees in 9 seconds. So that's something like this: 9, 8, 7, 6, 5, 4, 3, 2, 1. So that's very fast for something this size. In fact, one of the reasons why we couldn't build the LSST on a mountain in Hawaii is because the volcanic rock isn't strong enough to support a telescope that's doing this at such high speed. It would gradually dig itself down. Okay, so LSST very fast. We take a deep 20 gigabyte image roughly every 40 seconds. So it'll be doing this. It'll be pointing for 30 seconds worth of exposure, and then moving to a new point on the sky at about that speed, taking another image, and then moving on to the next one. And it'll do that every night for 10 years, building up imaging over the whole southern sky. Okay, I said something about a tertiary mirror a minute ago. Let me look at that in a little more detail. Here's a picture of the various optical elements of the LSST without all of that mount assembly around them. So here's the path that the light takes. So from celestial objects, off the primary mirror, which is the outer part of this big mirror down here, up onto the secondary down onto the tertiary, which is ground out of the middle of the primary mirror. That was nerve-wracking to do, but we managed it. And then the light comes up here into the camera. There's, I think, 3 corrective lenses that then take the light onto the focal plane into this camera, which is the size of a small car. So one of the main things to do, of course, is not to drop the camera onto the mirror. Right, I'll tell you that. Okay, so here's a picture of the mirror at its where it was made in Tucson at the Mirror Lab. Here it is again on the truck being taken up the mountain in Chile. So look how cleverly the LSST has been designed to just fit through the tunnel up to the mountaintop. So the good news is that the mirror's name is M1M3 for the primary mirror and also the tertiary mirror, the same piece of glass, M1M3. M1M3 made it off the ship at Cocambo and through this tunnel by the dam and arrived at the summit on May the 11th. So this is a major milestone. We managed to get this big piece of glass all the way from Tucson in Arizona to this mountaintop site in Chile without dropping it. Okay, here's another picture of the enormous mirror on a giant truck being towed up a mountain. And you can see just at the top here, here's the observatory. Anyone recognize this? Yeah, it's Gemini. This is Gemini South. Okay, let me tell you a little bit more about this camera. The world's biggest digital camera. I can't say that enough times. Some pictures for you from SLAC. Here's what the outer barrel of the camera looks like. Mounted, or it's going to be lowered into position, pointing downwards as it will in real life, observing down there the sky that's up there. And here you can see an upward view of the focal plane. So this has just one raft of sensors in it so far. By the time we're finished, this will all be full of CCDs. So this is a picture of what the eventual focal plane will look like. So 21 rafts of 9 sensors. These are all being assembled at SLAC at the moment. It has this nice modular design, so if a raft breaks, we can take it out, repair it, and put it back in again. And you can see here that each raft is made up of 9 sensors. Each sensor is about that big, and the whole focal plane is sort of that size. So it's an enormous camera. So we're still on schedule in construction here. First light will be sometime 2021, and the survey will start in the autumn of 2022. I want to say autumn because it makes me sound exotic. Okay, so you should remember LSST is a super fast survey telescope with pieces here. I like showing this picture. This is me back in 2008, where I was visiting the Mirror Lab in Tucson, and here behind me you can see the mirror when we started making it. So it's just had this mold here has been filled with chunks of glass, which were then slowly melted, and the mold was spun around in order to make a parabolic shape, and then the glass was cooled down and it set into a paraboloid, and then the central bit was ground out to make a spherical mold. And I was so pleased with being here that here I am having my picture taken. That's what I used to look like. Okay, so LSST will take a log, ship's log, of a 10-year voyage of discovery, imaging the entire southern sky every few nights over that period. So the result of all this imaging will be, for each point on the southern sky, a movie of about 800 frames. So you can see one of the things that we'll be able to do with LSST is not just take a very deep look at the universe by combining all the images together. We'll also be able to look at how things are varying in brightness with time over the course of 10 years. So here's a map of the southern sky. Here you can see where the galactic center is. And the parts shown in orange and yellow and red, this is the expected sky coverage after 10 years. Here's the ecliptic. The actual patch of sky we cover won't quite look like this. It's still being optimized for science, but it'll be something like this, half the sky with around 800 visitors. Okay, so what does it mean to have a 3 gigapixel camera this size mounted on a telescope with such fast optics collecting so much light? So that large number of pixels allows us to not only take wide field pictures of the sky, so something like 3.5 degrees diameter images, but it also allows us to resolve objects with a fraction of an arcsecond resolution. So what does that look like? Well, here's a familiar object, half a degree across. So this is just a small piece of the LSST field of view. And behind that area, this is what the deep night sky looks like. So it's the same area of sky, I've just taken the moon out of the way. And you can see here's a nearby galaxy. Most things here are galaxies that you can see. The stars are the ones with diffraction spikes and saturation trails and things. This is an image from the Canada, France, Hawaii Telescope Legacy Survey, which turns out to be similar in depth and sort of filter coverage, colourfulness, as the LSST survey will be. It's just over much less sky. Okay, so this is what the LSST data should look like. And this is a patch of sky about half a degree across. And this is a picture of a hair held at arm's length. So if we zoom in here, you can see here's a type of object that I'm particularly interested in. This is a gravitational lens. Here's a cluster or a group of massive red galaxies. And behind it, there's a faint blue galaxy that's being magnified and distorted into this amazing Einstein ring system. And all of that fits into this tiny box. And here's again this hair at arm's length. So we'll be able to take wide field images with very high resolution. That's what we're going to spend our 3 gigapixels on. Okay, so another way of thinking about what this means is to think about how much data a 3 gigapixel camera produces. So if we took an LSST image from the whole focal plane, the entire field of view, and we'd said, right, let's print it out at 72 dots per inch on your home printer, you would need a 70 by 70 foot square piece of paper, and then 3 tennis courts to lay it out. So imagine walking over 3 tennis courts, get down on your hands and knees, and you can see the smallest things resolved are the stars and all the galaxies. And that's just one field of view. There's about 2,000 fields over the whole southern sky. 6,000 tennis courts. Okay, so a huge sky area. Billions of objects, billions of stars in our galaxy, billions of galaxies outside our galaxy. And because we'll come back to each point on the sky around 1,000 times, 800 visits on average, what that means is we'll be making trillions of measurements of billions of objects. So we'll do this automatically rather than by hand. This is what the data facility will do. We'll be processing the images and making automatic measurements of things like the brightness of every object, the size of every object, the apparent size, the shape, the ellipticity we call it, and various other measurements that we can make just from the images that we take. And we'll do that automatically and produce a so-called catalogue of measurements that will look a little bit like this, at least when you query it from the database and display it like that. So there'll be thousands of astronomers looking at this catalogue of measurements and doing science projects with it. So that's where the synoptic part in the name comes from, Large Synoptic Survey Telescope. You've seen how large it is. You're familiar with telescopes. It's doing a survey, but the word synoptic means it sees everything, which is to say you can do lots of different science projects with the same database. So it's efficient in that way. Okay, so I thought it'd be interesting to tell you a little bit about the kinds of science questions we can try and answer with the LSST survey. And there's sort of 4 rough areas of astronomy that we can make a lot of progress with LSST. So one of them is taking a census of the solar system. So I'm not talking about observing planets in the solar system, I'm talking about observing everything else. So what do we expect to be out there? Something like 5 million main belt asteroids, 300,000 Trojans, they're the asteroids that follow the giant planets around. 100,000 near-Earth objects, so asteroids with potentially with our name on it. And something like 40,000 Kuiper belt objects in the far reaches of the solar system. Interesting things to study. And we'll see these as moving objects. If you're taking an image of the sky, and then you come back half an hour later and you take another image of the same patch of sky, you can imagine that the moving objects, you'll see that movement. They'll appear in different places between those 2 images. You can come back a few nights later and do another comparison, you'll see that moving object has gone over there. And you can start to piece together the orbit of all of these objects. So tens of thousands of solar system objects, each with an orbit that's mapped out by LSST. So here's an interesting thing that we might be able to do with such information. Imagine that if you can map out where all the Kuiper belt objects are, and you know their orbits, you can start to look for unexpected features in their orbits. You can start to look for perturbations, Kuiper belt objects being nudged around by other massive bodies that might be out there. We might be able to find the missing planet that we think was there in our solar system early on and got kicked out. So we can go searching for planet 9. I guess it used to be planet 10, and then Pluto got demoted. So now it's planet 9. So the models predict that it should be out there, and we can go looking for it with LSST. Okay, let's go a little bit further out, beyond the solar system to our galaxy, the Milky Way. We can do something similar. We can look at the distributions of stars, so where they are in space, in the sky, in 3D, if we have some way of estimating how far away they are. We can map out where the stars are and start to see features like stellar streams left behind as small satellite galaxies fell into our Milky Way as the whole system formed. So we can start to trace out where these streams are. We expect there to be quite a lot in the outer parts of galaxies. Here's a very deep image of a nearby galaxy, and look how much structure there is in the outer regions of it. Normally you don't see this stuff because you don't look deep enough to see those faint features. But if you take the time to go very deep with a big telescope, you can see these features in the outer parts of galaxies. And these are leftovers from previous collisions of galaxies to make this one galaxy that we're now looking at. So we can find stellar streams. We can then do something similar as we plan to do with the Kuiper belt objects. We can look for unexpected features in these streams, little kinks and wiggles in these streams of stars across the sky. And one way to make a wiggle like this, it might look something like this, okay? One way to make that could be another even smaller galaxy flying through the stream. And it may not have even been a galaxy. It could have been just a blob of dark matter without any stars in it. This is one of the few ways that we can see the effects of dark matter, even if there are no stars associated with that dark matter. So it gives us a new way of mapping out where the dark matter is, as well as where the stars are. Okay, let's keep going, exploring further out into the universe, beyond our galaxy, to look at all the other galaxies. So here's a model prediction of the kinds of patterns that galaxies make when you do a big sky survey. So you can imagine this to be a visualization of the catalogue of galaxies that LSST will observe. Each colored point on this picture, think of it as a measurement of position and brightness of a galaxy. We'll be able to make maps like this with the LSST catalogue. We can already do this with things like the Sloan Digital Sky Survey. We just can't go very deep out into the universe. We can't see even very faint galaxies. We'll be able to make maps like this out to the very distant universe. Why is that interesting? Well, again, we can start to infer where the dark matter must be. The idea is that the dark matter is falling together under gravity, and the stars that are there in galaxies within these dark matter clumps fall in with them. And so if you look at the pattern of where the galaxies are, you're seeing something about where the dark matter should be. How do we know there's any dark matter there at all? Well, it turns out that these clumps of galaxies are too heavy compared to what they look like. So they have a certain brightness, but they have gravitational effects that are too strong for what you predict just by looking at their brightness. And we'll be able to do this kind of statistical analysis of the clustering of galaxies and where the dark matter is and how much dark matter there is, how strongly it's clustered. We'll be able to do that over huge volumes of the universe. So here's a little picture for these gravitational effects. The main one we're interested in is called weak lensing. So I showed you a picture of a strong gravitational lens. Do you remember that? The group of red galaxies and had the Einstein ring around it. That's strong gravitational lensing, where they're obvious curvy arcs, very spectacular. Turns out that all of the faint galaxies in the universe appear to us weakly lensed, because we always see them through this haze of dark matter filaments and other galaxies. And so we always see their shapes slightly distorted, and we see them at positions slightly offset from where they should be if there wasn't any mass along the line of sight. So we can use this weak lensing effect to make another kind of map of where the mass is and get more information about where the dark matter is, and also how these clumps and filaments of dark matter have fallen together over time. Because when we look back at the most distant galaxies, we're seeing them as they were the longest time ago. And so if we focus our attention all the way back there, we're looking at the universe as it was billions of years ago. We can then compare that with what the universe looks like here. At a closer distance, we're seeing the universe as it was less long ago. And so we can compare what the universe was like then with what the universe was like nowish, and look at how structure builds up in the universe. And that turns out to depend on what the universe's expansion is doing. The faster the universe expands, the harder it is for structure to fall together, because it's trying to fight against the expansion. So we can learn about the expansion history of the universe by mapping out where the galaxies are, where the dark matter is, and where the galaxies were, and where the dark matter was.
In that picture, the kinky path won't do you much good unless you know what the straight line path would have been to compare it with.
Yeah, that's right. So this picture here, it's kind of a cartoon. So the deflections that you see here, each one of them is very small, but they can add up to something bigger. It turns out that a good enough approximation is to say, let's compare this with a light coming straight through, where just the shape of the galaxy whose light is shining gets changed. It's called the Limber approximation, and it turns out to be good enough for measuring the expansion of the universe. Okay, so why are we interested in the expansion of the universe? Well, it's because there's something about it that we don't understand. You may have heard this in many talks before, but just to remind you, here's what we think happened through the history of the universe. From the Big Bang here, going that way in time. So stepping through in time first, the universe cools, becomes transparent, then the first stars form, there's gravitational taps, you get galaxies forming, and then at later times, the universe, the expansion starts to accelerate. And that was the unexpected thing in 1998. No one saw that coming. And so we have this unexpected phenomenon to try and explain. So the universe expansion is accelerating, and no one knows why. It's maybe the biggest mystery in physics right now. It's comparable to being told your whole life that what goes up must come down. And then you find that when it comes to the whole universe, that isn't true anymore. Okay, so we have a goal with LSST, trying to measure cosmic acceleration to better than 2% precision. We can do it two ways. One is we can look at the objects like galaxies as they fall and try and understand the acceleration of galaxies that way. We can also try and measure acceleration in the universe by comparing actual distance to an object with how far it appears to be away. And so it's a bit like when you're on the streets of San Francisco, you know that cars have a certain brightness to their headlamps, and so you can imagine being able to estimate how steep this hill is just by looking at the brightness of the headlamps. So we're trying to do a similar thing with LSST. So one way we can understand acceleration in the universe is through this weak lensing effect, the growth of structure in the universe over time. The other way we can do it is by using objects that are whose luminosity we know. A bit like car headlights, we know how bright they are. Type 1a supernovae, we know how luminous they are. So we can see them at a certain brightness, we can make an estimate of how far away they were. And if we can do that for large numbers of supernovae, we can start to map out distance and acceleration in the universe. So, with LSST doing this immense sky survey over 10 years, we expect to be able to see and use something like 100,000 Type 1a supernovae. So objects that are relatively rare in today's astronomy become common with LSST. Okay, so as you can tell, I'm particularly fond of this use of LSST, doing cosmology with it. We do think we'll be able to get to something like percent level measurement of exactly how fast the universe is accelerating. And that's sort of the first step in understanding why it's accelerating, is to try and rule out what can't be going on. And the way to do that well is to have very accurate measurements of the actual acceleration rate. Okay, so I mentioned supernovae. The reason why we can see so many of them is because we're doing a wide area sky survey, but also doing repeated imaging over 10 years. So we get to see these supernovae as they explode and get fainter again. And we can measure those light curves, we call them, for 100,000 objects. You can imagine that we can do this with lots of other types of exploding objects. Anything whose brightness varies with time, we'll be able to measure how that brightness varies with time and start to understand all these different time variable objects or exploding objects, transient objects in the universe. So LSST will be very good at exploring this, not only the night sky, but also the time domain, the behavior of astronomical objects with time. So here's an interesting plot. This shows, for various exploding things in the universe, the duration of their explosion between one day over here and 3 months over there, and the luminosity or the intrinsic brightness of the object. Ignore the picture of the ship. Each point on here is a different type of object. So, for example, for those of you who can't read this at the back, we have the type 1a supernovae are up here.
Right.
Yeah. Thermonuclear supernovae, otherwise known as type 1a. There are other types of supernovae, core collapse supernovae over here. There are extra special supernovae up here, the ultraluminous supernovae. There are also things that look a bit like supernovae but aren't supernovae. So they're not entire explosions of stars, they're just sort of explosions on stars. And then down here, similar things, novae in our galaxy, and then classical novae down here. So over here, the reason why I put the picture of the ship here is because we don't know anything about what's going on here. So if we can study these transient events with LSST that have durations of a few days, and we can take images deep enough to go all the way down here, but also not saturate so that we can measure them up here, we can explore this whole ocean of possibility. So this is what we mean by LSST will open up the time domain, allow us to explore the universe in ways that we just haven't been able to before. So a good question for us is, what happens when black holes collide? We keep hearing about this in the news, right? Every few months there's a black hole collision and the gravitational wave detector goes off. What we'll be able to do with LSST is go looking for little flashes that correspond to those black hole collisions that we see with gravitational wave detectors, and ask, well, did anything happen? Was there a flash of light at the same time? If there was, we'd start to learn something about what's going on, the physics of black hole collisions, or what happens when black holes collide. Okay, so hopefully that gives you some flavor of the kinds of astronomy that we're excited about doing with LSST. It's not just me that's excited. Here we have hundreds of scientists and engineers and support staff. This lot in identical t-shirts are the ones who are involved in either building the LSST or getting ready to operate the LSST. So I'm somewhere at the back getting ready to operate it. Over here, this is a large group of cosmologists getting ready to make high accuracy measurements of the expansion of the universe with LSST. Also hundreds of us here, and I'm somewhere there, reclining. So this is the Dark Energy Science Collaboration. It's 900 scientists, big international group, all of us trying to work together to measure the universe in various ways using LSST. It's big science. Okay, so LSST will make many different maps of the universe at different scales, also not just in space but also in time, in distance out into the universe as well as across the sky. So many different maps, and we said at the beginning that maps are useful for other people to follow. Once you've got a map, you can go exploring the ocean. So, who's going to be using those maps? Well, all the other astronomers in the world will benefit from the maps that LSST make, and that includes all the people who don't get paid to do astronomy, a day job, but are nevertheless interested in doing astronomy. So people like you. So one of the things we plan to do as part of the LSST system is enable citizen science projects that use the LSST data. There's just too much of it for the professionals alone. We're going to need a whole lot more people looking for unusual, unexpected things in the data in various ways. So the way we can do that at the facility is not by running lots of projects, it's by enabling scientists to define projects that they then carry out with all of you, if you have time. So here's an example. This is a citizen science project that I helped lead. This was looking for strong gravitational lenses in LSST-like images. So you can imagine going to a website and being shown small images of the sky and being asked, given your experience and expertise with strong gravitational lenses, do you think this is a lens or not? Turns out that the 36,000 people or so that take part in this are pretty good at it. And they're good at help finding and spying lenses. You can even go to this website. I'm not sure how much data we have there at the moment, but it might give you a feel for the kinds of things that we'll be able to do with LSST. So, like I say, we're hoping to make it, well, we will make it possible for scientists to define projects. This is what it looks behind the scenes, setting up a project. There's the interface for actually building the thing. And I think one particularly interesting possibility is opening up this interface for building a citizen science project to the citizens. I mean, it's not like professional scientists have a monopoly on ideas. There's lots of things to explore and not enough time to be done. So I think the more people we have actually doing science investigations, thinking about questions about the universe and then exploring them, the better. Okay, so all this is a far cry from the first explorers to reach America. Not Magellan and his crowd, there were people exploring America long before that. I didn't get to go to this place in Arizona when I was last there, but I will go at some point. Turns out there's a Clovis site near Tucson that has the fossilized remains of a mammoth kill. So the Clovis people were early Americans, walked here over the Bering Strait, we think, and were living in North America from about 10,000 years BC. So these are very interesting people. Not, well, a bit further back, but not that much further back. People similar to the Clovis people in Germany were doing the same kinds of things, hunting mammoths, gathering berries, that kind of thing. But also, apparently, making carvings of mammoths. Isn't that amazing? I didn't know this until I started writing this talk, that people 35,000 years ago were making representations of mammoths. Why were they doing that? Why would you make a model mammoth? They must have been trying to tell each other something. They must have been hunting mammoths and then telling each other about it. They must have been exploring the countryside, looking for mammoths and berries and things, and then communicating with each other about where to go to find mammoths and berries. So they were already making maps of the kind we've been talking about all this time ago. So there's something very fundamental about exploration for humans. We have always done it, apparently. We've always been gone exploring. We've always made maps to tell each other about what we found. In fact, I think it's fair to say that exploring is what humans do. We do it naturally. You know this from being out at star parties and people asking questions and wanting to go look at the next thing, and then the next thing and the next thing. They're literally exploring the universe with you. So here's another natural explorer. A friend of mine sent this to me last week. This is, my friend works in a kindergarten. This is Miriam, age 5, and they've been studying space at kindergarten. And this is the painting that Miriam drew, and I asked permission to show it to you, so I thought it was cool. Miriam's clearly very excited about space. What she's painted here, she hasn't painted a picture of the universe. That would be very dull, right? It would be mostly empty space with some bright points of light in it. Instead, what she's painted is a picture of things we know about the universe. This is really cool. She explained it to Brittany, that she's painted a picture of stars, some of them bright, some of them faint. She's painted galaxies. She's also interested in planets, the planet section. She's a fan of NASA. But she painted this picture just to get down everything she knows about space. She just wanted to have it on the page in front of her, as if she was making a guidebook for herself. So I think Miriam is primed to go exploring the universe with LSST. She's got everything down, like what does she know? I know about planets, I know about stars. Now I'm ready to go follow the map that LSST is about. So the last thing I'll show you, there are people at the LSST in the Education and Public Outreach Department who are preparing to help natural scientists like Miriam explore the LSST data. So they are making activities for use in the classroom, not so much to teach the specifics of astronomy, as much as just help kids in school find some direction to their natural explorations that they want to make. So making classroom activities based on the LSST data is one of the things we're very excited about. Okay, and just to show you, we plan to show a fraction of the LSST data in a special web interface for the public, for people like Miriam to explore, people like you as well. It'll look a bit like the Sloan Sky server, but allow you to explore what has been found in the LSST data so far. And I'm hoping this will be a very useful resource for all kinds of astronomers. I think this, before it became a PDF, this talk was a PowerPoint talk. And when it was a PowerPoint talk, some of these stars would twinkle. You can imagine that, you know what a twinkling star looks like. So I wanted to finish with this slide just because, to come back to this point about humans being natural explorers. We do it without thinking, but it's interesting to ask, well, why are we explorers? Why? Part of the answer to that is, well, we evolved that way. We are hunter-gatherers. We're not hunting and gathering mammoths and berries anymore. We're hunting and gathering information. But what is it that allows us to do that? Well, all of us have it. It's the sense of wonder you have when looking at either astronomical data with LSST or through a telescope as you do at star parties. And you already know, this is why I like talking to amateur astronomers, you already know that everybody has that sense of wonder when you show them the sky through a telescope. And hopefully everyone will have it when exploring the LSST data as well. Okay, thanks very much for listening. Well done, you people who like to ask questions during the talk. I saw you sit like this. Now you get to ask questions. Hi. Yeah.
One question I have, since you're going very deep with the telescope and with the sensors, how do you deal with the dynamic range of these photos?
It's a good question. So the question was, how do we deal with the dynamic range in these images because we're going so deep? Well, the sensors themselves are not very different from the CCDs that are on regular telescopes. They're a bit different, but mainly they're different in their sensitivity in the infrared rather than in the optical. But other than that, they're CCDs. So it's the same dynamic range that we deal with all the time with CCDs. Particular problems for LSST are that because the telescope has a big mirror and we're trying to go deep, if we take exposures that are too long, then the stars start to saturate too fast. So one number to have in your mind is that the stars in LSST images saturate if they're 17th magnitude or brighter. So that's fairly faint. It means it's hard with LSST to study stars that are brighter than 17th magnitude. So that's one way of saying that's our solution to the dynamic range problem is to focus on the faint. Hi.
Yes, so what would be the focal ratio of the primary? Like F1 or something?
Okay, it was another question about focal ratios, and I already revealed my ignorance of that at the beginning. I don't know. I have to look it up for you. I know that it's fast. I know that the focal ratio are all close to 1, but I need to find the exact numbers for you. What I should have done is look them up in advance because I knew that there would be astronomers here. Yeah.
I believe I read 1.8, but
Sorry?
I believe I read it was 1.8, but I'll check.
1.8 for the primary mirror.
1.8?
That's what I remember seeing some time ago.
Yeah, at the back.
Is there a computer program, I don't mean a computer program, just a program using computers to real-time find these nova so that you can then say, all right, we found this, and then point it off to someone else to get the light curve, or are you going to be able to do all of that yourself? You're not going to change the survey schedule just because you detected something, right?
Good. So the question was, is there a computer program, an automatic pipeline for detecting these novae and other transient events? Or will we have to do it ourselves by downloading the images and go looking for them? It's the former. Because the data will be coming in so fast, we need to use the supercomputing facility to process it and feed out these transients for other people to study. So we don't have any choice. It has to be automatic in order to keep up with the telescope because it's so fast. So what will happen is the images that are taken on the summit will come down to the base at La Serena and then up through optical fiber to Illinois. And they'll arrive within a minute of being taken and be processed as we go, and novae and other transient events automatically detected. And when something has changed in the sky, an alert will be sent out. And there'll be a lot of alerts because we'll see lots of changes in the sky. But that will provide a stream of data that astronomers outside the facility can sort of plug into and then start filtering to find the things that are actually novae. So it won't be the case that we'll be able to filter these transients for you and be able to say, this one's a novae, this one's a 1A, this one's a 1A, this one's a 1A. We won't be able to do that, but we'll be able to say, there was a transient here on the sky and it has this brightness and this is what it looked like for the last month. And do that for all of the millions of transients a month. Okay.
Well, what I was wondering is, You know that big camera that you were using for taking a picture of the sky, you know? LCCD, right?
It's
LSST.
Yeah.
LSST. Well, which has a better zoom? That would be what?
Which has a better zoom, LSST cam or the James Webb Space Telescope?
Yeah.
So
They're
let's.
both effectively for telescope purposes, correct?
Yeah. By zoom, do you mean which one can take sharper images of small things?
I mean, which one can take a reasonably clear image from the farthest away?
Okay, so I think for angular resolution, that is seeing very distant things and still being able to make out how big they are,
Yeah.
the James Webb Space Telescope will be better for that.
How about as the general focus, like how clearly you can see an object? Would that be that or that?
So it's still true that the James Webb Telescope will be higher resolution. So when you're in space, there's no atmosphere to make the stars twinkle. There's no blurring due to the atmosphere, and that's why the images are sharp. But the LSST, if the LSST was in space,
It would be better.
it would be better because the mirror is bigger. But because the James Webb Space Telescope is a space telescope, it will make sharper images. Both of them will have less resolution than, let's say, the 30-meter telescope.
30 meter, which one's that?
Ah, well, you should get someone in to give you. We have to get Oh, okay. So the TMT talk is on the way. So that's the one to come for extreme resolution.
TMT?
TMT. Yeah.
I want to ask you a question. First, let me lay a foundation. I know that if you want to get faint, the signal increases linearly and noise increases as a square. So how do you know when to call it quits? If it was film, you could say, well, the film got saturated, so I'm going to call it quits. But with a CCD, you can't fill up the computer. So how do you know when to call it quits?
Yeah. How do you know when to call it quits? How do you know when you've gone deep enough it's not worth going deep anymore? So it depends a little bit on what you're trying to measure. So it turns out for cosmology, before you get to the limit of the noise getting in the way, the other galaxies in the universe get in the way. So with LSST, we'll look so deep that, you remember I showed that picture of the outskirts of galaxies and how complicated they were? But imagine seeing something like that for every galaxy on the sky. You can imagine that they'll all start blending together. We say blending. And so that makes it difficult to make high precision measurements when everything's blended together. And so that's more of a limit for us. So if we were to go deeper than 10 years worth of added up images, it wouldn't really be worth it because we'd just be we'd still have the blending problem to deal with. So there'll be similar considerations for the other science projects as well. And it turns out that 10 years is about right for a sky survey with LSST. So you might then ask, well, what are we going to do with this $1 billion telescope after 10 years? So we started thinking about that. I think the basic answer is we should try and do something different than what we did in the first 10 years. So maybe we should make different filters and do a sky survey again, but with different filters. That might be a good way to go. We could try and put some kind of dispersive element on there to get more spectroscopic information. You could imagine, at great expense, building a different camera that had different properties. And so all of these ideas will get sort of thrown around over the next few years, and we'll come up with a plan by around 2025. Are there any questions from women? Very male dominated. I'd like to give a pause. Yeah.
Okay, so you described about doing surveys of the solar system as well.
Yeah.
So my question is regarding interstellar visitors. We had one recently. So will the survey also look at potential sightings of interstellar visitors so we can point all the risk telescopes on that thing and
Yeah.
take them earlier?
Absolutely. So when doing a census of the solar system, I mentioned looking at all the Kuiper objects and looking for objects that have odd orbits. Well, interstellar visitors are great examples of things that have strange orbits. And so we should see more things like that. Nomads of the galaxy, roaming from star to star, bringing their viruses with them.
What do you want us to do in this survey? There going to be projects out there we can log on to and do? And
yeah, there will be. So what do we want you to do? So I think the first thing is, this age of social media, follow us. So just follow along with how the project is doing and watch out for news about citizen science projects. That's the key word to listen out for, citizen science. Those are the web-based things where eventually we will need help from people like all of you. It's too early to say what those citizen science projects will be. I think what will happen is we might have one or two ideas to get started, but the really interesting ones will come after we've all had a chance to look at the first data. So as you're following LSST, follow us all the way through to the start of the survey and the first data, and start thinking about what's there in the data, and then watch out either for citizen science projects that are set up asking for help, or maybe think of ideas for citizen science projects that you could suggest. I think it would be really neat for us to be doing projects like that. And I think people at clubs like this that already have a lot of expertise with practical astronomy and have spent a lot of time thinking about exploring the universe in various ways, there's a real opportunity to come up with science investigations of your own that we could build using this interface.
Is there a northern hemisphere equivalent to this? And if so, where would it be? Or located?
Okay, there is not a northern hemisphere equivalent of this. Every now and again, someone suggests, half-jokingly, what should we do in the second 10 years? Move the LSST to the north and complete the job. So far, there's no real plan for something quite like LSST in the north. But we can't not survey the sky anymore. That would be great. So instead, what people are doing is piecing together a survey similar to LSST's from a number of different telescopes. So the people at NOAO in Tucson are interested in doing this. There are surveys that are shallower, lower resolution, but still have the similar sky coverage. So there's pan-stars, there's the dark energy survey goes a bit north, there's the imaging that the DESI survey used. All of that can be combined in various ways to piece together a survey in the north. And for a while, that's the best we'll be able to do. Yeah?
Where did most of the funding come from for this survey?
Where did most of the funding for this come from? It's a joint project between the National Science Foundation and the Department of Energy. The NSF built the telescope and the data processing system, data management system. The DOE built the camera. And it's interesting to think about why. The DOE tends to do particle physics projects. The DOE thinks of the LSST camera like a particle physics detector. It's like a detector that instead of having a particle accelerator like at CERN, it has the universe firing photons into it. But it's a big detector that will produce data that cosmologists, fundamental physicists like me get to use. And so that was the DOE's interest in building the camera. And so they split the cost something 3 to 1, something like that. NSF providing the lion's share.
Yeah. Just for everybody's information, there is an unbelievable book called Over the Edge of the World, or maybe Over the Edge of the Earth. It's about Magellan's voyage, and truth is just absolutely stranger than fiction. You won't believe what they went through. It's about the voyage of the 5 ships and how they kept losing them, and it's just amazing. It's a fascinating book.
Over the Edge of the World, did you say?
I think it's Over the Edge of the World. I'm going to look it up right now.
I should buy it for Melinda for her birthday.
Oh,
and then read it myself.
Great.
I think we're going to want to have you back, in the next few years.
I would be very happy to come back and give you an update on how LSST is.
And I want to give you a token of art. Thank you.
Oh.
Well,